Hello and welcome back to Unit 9. In the second part of Unit 9, we are going to define the physics concept of impulse. In the last section, we showed how with Newton's second law, we could get to this formula, where the net force multiplied by the differential element of time is a small change in momentum, a dp. And I'm going to define this as a small change in a quantity given by the letter J, where J is impulse. Okay, so what is impulse? It's what happens when momentum changes. Okay. In general, it doesn't have to be a net force that causes an impulse. It could be any force, and then we'd have to add all the impulses up to figure out what the net impulse would be. But to find the impulse due to any force, I would have to integrate. So J will equal the integral of f dt. Okay. And that integral will run from time t1 to time t2. With a little bit of work and some algebra, we can write that J is, in general, the average force acting on an object multiplied by the change in time. Okay. If you want to see how to go from here to here, I'm going to refer you to your book. Look in your book. However, if the force is constant, then it can pull out of the integral. So this now just becomes f times the integral from t1 to t2 of dt. But that is just f delta t. Now to derive this, I lost my little arrows here. To derive this, we've assumed that f was constant, but as we just saw, this is true for the average force. If we also assume that the force involved is the net force, then that can be written as ma times delta t. And then I can write this as m delta v over delta t. And that lands me at my impulse is the mass multiplied by the change in velocity, which, if you think about it, kind of where we started when we first wrote down the definition of a small piece of impulse. It was an f net times a dt, or it was a little change in momentum. Okay, so why are today's cars designed to crumple upon impact? Well, this is a question about impulse. Why is it being fussy? Okay, here we go. So impulse is going to equal the average force multiplied by a change in time, or it's the change in momentum. Okay. Let's think about this aspect of the impulse equation. Okay. The change in momentum is going to be determined by the parameters of whatever collision is going on with our car. So we would have mv final minus mv initial. Well, the initial velocity is whatever the car was doing before the collision, and the v final is whatever it's doing after. Maybe it came to a stop. But this is fixed by the parameters of the collision. Okay. On the other hand, if we look at this portion of the equation, while it has to equal the change in momentum, we have control over it. If we take this and say we're going to make delta t really big, then the force becomes small. So that when we multiply these two pieces together, we get whatever that change in momentum is. Okay. So why are cars designed to crumple upon impact? For exactly this reason. We can't control the change in momentum. The collision is the collision. What we can do is extend the amount of time it takes for the collision to occur in order to decrease the force that acts on the person. This principle is the same as how seatbelts work, because again, you can't control that. However, you can control whether you hit the steering wheel with a very, very, very short amount of time, therefore making it a large force, or not. Lastly, in this section, we are going to work on this example. In this example, we have a ball colliding with a wall. We're given the mass, the initial speed, and the collision time. And we want to know what are the force and what are the impulse, or what is the force and what is the impulse, if the ball rebounds versus if the ball sticks. So if we think about part A, we have our ball coming in with a velocity v and exit with that same velocity. And part B, it comes in with that velocity b and then it sticks. It's just there. Okay, we're going to work this all in a one-dimensional manner here. To find the impulse, I need to look at the change in momentum. And the reason I need to look at the change in momentum is because I don't have the information to use the force multiplied by change in time version of this problem. So that will be mv final minus mv initial. And because it's vectors, I need to define a direction of positive. So I'm going to let the initial direction of the velocity toward the wall be positive. So the change in momentum will be a negative mv minus mv, or negative 2 mv. And if I plug numbers into this, it works out to be negative 3 kilogram meters per second. And that is my impulse. To find the force, I'm going to use that the force multiplied by the change in time is the impulse. Again, plugging in numbers, that gives me that the force is negative 3,000 newtons. For part B, my change in momentum, again, will be mv final minus mv initial, which in this case will be 0 because we're not moving at the end, minus mv, which is negative mv, which will be 1/2 of what I had in the previous part. My average force will then be the impulse divided by time, which will be negative 1,500 newtons. This concludes this part of this unit.